বলছে। Welcome to this first live session on this NPTEL course on stereochemistry. So, today we will be discussing some of the questions that has been put forward in the discussion forum, and I have with me one of my TA, Ms. Monisha Singh, and you can post the questions online from now on. Okay. So, I will start with the questions that we have received so far for the live session. Okay. So, the first question that was by Shubhangi Nath, and she is asking how to convert Sawhorse to Newman configuration. Okay. Now, I will just slightly rephrase the question, that is how to convert Sawhorse to Newman projection formula. These are projection formula. So, that is the question, that from Sawhorse to Newman. Now, you know what is the, it all started, the projection formula all started with Fischer projection, then Newman projection and Sawhorse projection. So, these are the projection formula, and there is a 3-dimensional formula which is called the Wedge formula. Okay. So, these are the 4 different types, but the projection formula is the Fischer, Newman and Sawhorse. Now, how to convert is the question is basically how to convert from one to the other. Now, specifically she is asking that from Sawhorse to Newman. Okay. Now, let me draw a molecule in the Sawhorse. Okay. So, this is the antiform of Sawhorse. I think it is clearly. So, suppose this is number 1 group, this is number 2, this is number 3, this is number 4, 5 and 6. So, now you have to write the Newman projection formula. You have to also number these 2 carbons, because they will make the backbone of your Newman projection. Okay. That CC bond which are eclipsing each other. So, now suppose this is, so we are left with which numbers 1, 2, 3, 4, 5, 6. Suppose this is number 7, this is number 8. Okay. So, now you suppose you look from here. So, what will happen? You are seeing the number 7 carbon at the top, that is number 7 carbon, and you have the number 8 carbon at the back. So, we are looking from this side. Okay. We are looking from this side and number 8 at the back. Now, when you look from this side, 5 will go downwards. So, once you are correct with one of the bond, then the other 2 is becomes easy, because in the projection they make 120 degree. Okay. And then you look at the number 8. So, number 8 is here, that is the back carbon, and you see the number 1 is going at the top. So, here I complete this, the 5, and then it is 4 and this is 6, and here I have 1, and then the other 2 will be making 120 degree angles with 1. So, that will be now, this will be, because you are seeing from this side, 2 goes here and 6 and then 3 comes here. Okay. So, this is the Newman projection of this Sawhorse. The Sawhorse, which is the molecule which is represented in Sawhorse. Okay. So, basically what you see, it is you have to look any of these along the carbon carbon bond and then draw accordingly. You have to fix one of these bonds. Once you fix one, then the others are very easy. My suggestion is that always fix the bonds which are going vertically upwards or downwards, then it becomes easy. The other 2 bonds, again I repeat, these are all 120 degrees. So, once you fix one bond, then the other bonds are automatically fixed. Okay. So, that is the first question. Now, the second question is from Harpreet Kaur, a faculty, that is what is written. It is regarding the conversion of Wedge formula to Fischer projection with 2 chiral molecule. Now, the question is again, I will just rephrase the question. What I understand here is that that you want to actually convert the wedge, a molecule which has got two chiral centers, and you want to draw the convert the wedge formula, which is already represented in wedge formula, and then convert it to the Fischer projection. I think that is because two separate chiral molecules means two separate wedge formula and two separate Fischer projection. So, the question should be, as I understand, it should be conversion of wedge formula to Fischer projection for a molecule with two chiral centers. Okay. So, let me draw it here. So, I draw the wedge formula of a compound. Wedge formula means you have the alpha, beta, the concept. So, suppose this is your beta bond, this is the alpha bond, and there will be another one which will be in the plane. Suppose this is your x, this is your y, and this is the z. So, these are the three substituents, and then you have a carbon bond, and in this carbon, suppose what happens? Suppose this is your beta bond, and this is the alpha bond, and another one will be in the plane. Okay. So, let us put some arbitrary substituents, say A, this is B, this is C. Now, you have to, your question is how to convert it into the Fischer projection. Now, remember, in Fischer projection, the wedge formula that can be directly converted into the Fischer projection is basically an eclipse form. That means, the horizontal bonds should be both beta and the vertical bonds. So, these are the horizontal bonds, and this is the vertical one, and this is the vertical one. This is along the vertical axis. Okay. So, this is, so that means you have to convert this into that one, and then you can straight away draw the Fischer projection. Okay. So, how to do this operation? So, what you do, there are two ways to do that. One is you turn it little bit. See, you turn x little bit down, so that z becomes up, but this is not any 180 degree, it is not more than 90, it is much less than 90. It is about, say, if you turn it by say around 20-30 degrees, then what happens, x still remains beta. So, I turn it suppose by 30 degrees, and I turn it in a anti-clockwise direction. So, if I do that, so what happens if I do that, then x goes is still beta, but it is not that far away from the carbon, it is slightly beta, and then in the process you have made z also beta, because z has come up little bit, and y still remains alpha, because the angle of rotation is around 20 to 30 degrees, I said 30 degrees. And then, so basically now you have this one form at least is fixed, that both the horizontal bonds are beta, and here what you do, in order to make A little, because A is in the plane, to make A beta, A in the beta phase as a beta bond, then you turn little bit in the clockwise direction. So, this one in the anti-clockwise direction, and this one slightly clockwise, okay. And that will make the A beta, B still remains beta, and this is alpha. Okay. So, alpha beta nature of these bonds B C or X Y are not disturbed. What are you doing by this operation? You are making Z, which was in the plane, and A, which was also in the plane, you are making them also in beta. So, if you have this form now, it is now straight away you can write the Fischer projection. So, Z on this side, X on this side, Y here, C here, A here, B here. Okay. Now, that is one way of doing. There is another way of doing it. Now, I just suggest whatever is comfortable to you, you do that, but I will show the other. So, again I draw this wedge formula y, and this is z, this is x, and then this is your b. I draw the same molecule in the wedge formula, okay. And then what I do, I number it now. Suppose this is C1 and this is C2. Now, I individually draw the Fischer projection. I draw the Fischer projection of the individual carbons. So, if I draw the suppose the Fischer projection of C1, the carbon 1. Now, if you have gone through the video lectures, there I said that to convert from the wedge to the Fischer projection, it is better to look from the at the bonds which are having same similarity, which is having similarity means it should not be that you look from a beta and in between beta or beta and alpha. You can look through the bonds which are both in the plane. If it is written that 2 are beta there, so you look through the that angle which is created by these 2 beta bonds. Here it is beta, this is alpha, this is in the plane and that is in the plane. So, what I am suggesting you look from the look at the C1 from this side, because these 2 are in the plane. So, if you do that, you can now get the Fischer projection of C1. So, this is your 1, this is your 1, okay. And what is the this is your. So, what will be the Fischer projection of this? So, that will be going to the right Z, and this C2 is going to your going downward. Sorry, I am sorry. This C2 is here. C2 is on the left side. On the top is X, and on the bottom is Y. Okay. And Fischer projection formula of C2 is, now from where you have to look? Now you have to look from this side, because these 2 bonds are in the plane. So, when you look from this side, then what will happen? You are looking from this side. So, now what is seen on the right from this side, that will become left, and this A will become right as you are seeing from this side. So, A will now become on the right, and on the left will be C1, and what will happen? B will be at the top, because it is facing towards your head, and C will be at the bottom. Now, what happens? Because in the Fischer projection you have 1 here, 2 here, but here you are seeing that C2 is kept in the left hand side in the horizontal direction, and here C1 is also kept in the horizontal direction. So, in the Fischer projection what you have to do? You have to now do some conversion. That means, for the carbon C1 your 2 is at the bottom, and for the carbon C2 C1 is at the up. So, you just do the exchange in a group of 3 to bring C2 downwards. So, what you do? C2 bring C2 here, and then Y goes there, and Z. This is the your exchange in a group of 3 rule. So, that is your 1 carbon, and in the C2 you do the same thing. For C2 C1 is at the top. So, bring C1 at the top, and then B here, A there, and C will be here. Okay. Now, you just draw the anyone. See, now you have this at the bottom at the, this is your 2. So, C1 connected to C2. So, you just write this is 1, this is 2, and now X, Y, Z, and this will be your A and C. Okay. So, these are the 2 ways. One is by rotation. If you are comfortable with the 3 dimensional movement, you can write it, then that is okay. Otherwise, you can do this individual Fischer projection, and then for C1 you bring the C2 downwards, and for C2 you bring the C1 upwards. Then you just join these 2. Okay. That is the second question. The third question is by Debashree Odhikari. Is very good rule applicable for flying wedge projection? That was the question. Now, flying very good rule is, what is very good rule? Very good rule is that if you have a Fischer projection while doing the RS nomenclature, if your 4th group is in the vertical direction, and suppose this is 1, this is 2 and this is 3 according, this is at the priority sequence. Okay. If that is the case, or it could be 4 here, 1 here, 2 here, 3 here. That means, if the fourth group is occupying the vertical positions, that means these are alpha bonds. That is the direct wedge formula from the Fischer projection. So, that will be your 3, that will be your 1, that will be your 2, and that will be your 4. Now, what RS demands? The RS nomenclature, while assigning, you have to see to the carbon away from the fourth group. Away means the carbon should be below the plane of the, because we are seeing from the above the plane. So, the fourth group should be at alpha position, that is below the plane. So, very good rule means, if you put in the vertical direction, that means both are alpha. So, if 4 is here, whatever you are seeing here 1 to 3, that is your absolute configuration. In this case also, whatever you are seeing, because fourth group is alpha. So, 1 to 3 is the absolute configuration. So, that is very good rule, and this is only applicable for the Fischer projection formula. From the wedge formula, there is no very good rule as such, okay. But you can always extend it. If you see the fourth group in the alpha position, then you can directly do, like here 1 2 3 from the Fischer projection, and here it is also you can do it, but you have to make sure that your fourth group is in the alpha position. So, that could be the very good rule alternative of flying wedge. Very good question. Okay. And the next question, I hope this is clear, whatever I have said, is by S. Kishore. Sir, please give the brief summary or any study materials for how to calculate the Gauss-Butane interaction in mono and disubstituted cyclohexane. Okay. Now, the study materials will be provided very shortly. All the lectures now, the note form is ready, as well as the verbatim copy. So, that will be provided to you. Whatever we have said in the lectures, that have been concised and important points have been highlighted. So, that will be provided to you, but right now what I am trying to again discuss is that how to calculate first the number of butane interactions in substituted cyclohexane. Best is to start with the plain cyclohexane, no substitution, or your question is mono and disubstituted. Okay. We will start with a cyclohexane which is in the chair form, okay. And then put a methyl group here, suppose this is a methyl, and then what happens as you put, in cyclohexane, suppose this is your number 1 carbon, 2, 3, 4, 5, 6. Already without the methyl, the cyclohexane has 6 butane units, like 1, 2, 3, 4, that is 1 butane unit, 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 1 and 5, 6, 1, 2. So, these 6 butane units are there in cyclohexane chair without any substitution. As soon as you put a carbon, so now your number of butane units, you are now incorporating 2 additional butane units. One is this methyl, then C1, then C2 and then C3, and the other is methyl, then C1, then C6 and then C5. So, these are the additional butane units. Now, the question is what are the nature of these butane units? Are they eclipsed, are they staggered, or anti, or are they in the Gauss form? So, what is a Gauss form? That you have to calculate, you have to see the dihedral angle between this carbon carbon bond and this carbon carbon bond. And in the molecule you can see that this is actually not anti, because the anti direction goes here. This is not eclipse, because the eclipse direction goes in this direction. So, the other alternative is Gauss. So, that is in the Gauss form, and if you do the same argument that to make it anti, that should go in this direction, to make it eclipse, that should go in this direction. So, the other form is has to be Gauss. So, here the dihedral angle between this carbon carbon and this C5 C6 will be there. Now, so that means you are adding 2 butane units if you have an axial methyl, and that both the units are in the gauche form. So, that gives an extra energy 2 into 0.9 over a cyclohexane chair, 0.9, that means 1.8 kilocalorie per mole. Okay. And if you can see the model, if you can see the model, just this is your cyclohexane, suppose this is your all carbon, right, that is okay. So, this is your cyclohexane chair. Okay. Again I show you the model, first I have explained without showing the model. So, now this is the chair form, I think I will just keep it in such a way that you see the chair. Okay. So, this is the chair form, okay. And where is your methyl? The methyl is here, okay. Methyl is here. Now, let me see, I have to adjust it a little bit, yes. So, this is the molecule that we are talking about, an axial methyl group. Okay. Now, the extra butane unit is between this going to this carbon, then another carbon, and finally, this carbon. So, now the next thing that you have to see is the diagonal angle between this carbon carbon and this carbon carbon. Now, to do that you have to rotate it and then see in the Newman projection. So, you see it is 60 degree. The angle I am talking about is the one which you are seeing now, from this to this blue one, that is 60 degree. So, this is in the gauche, and the same thing happens with the other side also. The other side means this side. I have just taken from this side, you can also go from here to there, that is also in the gauche form. Okay. So, that is for one axial methyl. Now, if you introduce an equatorial methyl, then that is here. Okay. I change it. So, this is equatorial methyl. Now, the number of butane units remain the same, the additional butane units. Okay. That is this carbon, and then this one and that one, and then this carbon, that is this one and that one. Interestingly, in this form, if you look at the Newman projection kind of thing, see, you see this carbon carbon bond is now anti to this. Okay. And the same thing happens, this carbon carbon bond is anti to this. So, that means these two, an equatorial form also introduces 2 butane units, but these butane units are in the anti forms, and that is clear from here also, that one and that one, they are anti to each other. So, that does not introduce any additional energy as relative to the cyclohexane. If it is dimethyl, you have to be a little careful. When it is dimethyl, let us take the say suppose 1,2 dimethyl system. This is 1,2 dimethyl system. Now, whether it is cis and trans, that you have to see that what is the nature of these, things, okay, whether they are alpha or beta. So, if you hold it like this, you see this bond is alpha and this bond is beta. Okay. This is alpha equatorial, this is beta equatorial. Now, if I ask how many additional butane units are there, one is that if you incorporate one carbon, that immediately causes generation of 2 butane units. Okay. So, this will create 2 butane units, I can show it here. So, when you have this is the situation. So, if you have this methyl, so what happens, you are creating butane units. One is for each carbon, each methyl you are creating 2, that means this is 1, suppose 2, 3, 4, 5, 6. So, what will happen, one is methyl C1, C6, C5, another is this methyl, then C2, then C3 and C4. This is for this methyl, and for the other methyl you have CH3 methyl, then you have C2 and then C3 and C4, and you have CH3, then C1 then C6 and then C5. So, these are the additional butane units, but these additional butane units, but there is one trick, one we have overlooked, and that is the mutual butane unit that is formed because they are 1 to, they have a 1 to relationship. So, you see another butane unit here, so which is methyl, then C2, then C1, then another methyl. So, do not overlook that you may overlook here. Okay. This extra butane unit is not occurring if the methyls are 1-3 relationship, are in a 1-3 relationship, because the mutual thing is not there, they are not 1-2, it happens only in 1-2 system. Okay. So, what is number of additional butane units here? 5, that means in 1-2 system. Okay. How many are in the gauche conformation? This is anti, this is anti, this is anti, this is also anti, however, this is in the gauche form, okay, because the mutual one is having an angle of 60 degree dihedral angle. If the methyls are here 1-3, so then there is no mutual butane unit. So, additional butane units will be, for this methyl there will be 2 and for this methyl there will be 2. So, the additional butane units will be 4 and everything, because they are equatorial. So, everything will be anti to each other. Okay. So, one methyl group. So, we have just received a question. Here you said on addition of one methyl group to additional butane, gauche interactions are introduced, but in assignment answer it is given that no additional gauche butane interaction are introduced. How? See, the one is two additional, you have to see, if I ask you the number of butane units or number of butane units are introduced, that will be, that is just I have shown that if you put one methyl, forget about axial or equatorial, you are introducing two additional butane interactions. Now, whether they are in the anti or they are in the gauche, that is the important thing. So, when you put, it will definitely, introduction of one methyl incorporates two butane units, two additional butane units. So, that is correct, but in the now you have to see whether they are in the anti or they are in the eclipsed or they are in the gauche. So, if you in that case it has to be, if the methyl is axial, then the gauche, the butane units are in the gauche form. If the methyl is equatorial, the butane units, there is again there are two butane units, but that is in the anti form. That what we meant actually. Okay. Okay. Now, let us continue with that other question. Now, Monali, I think she has just said RS nomenclature. So, whether you have some problem with RS nomenclature, it appears that you have some problem with assigning the RS nomenclature. Okay. Now, here you have said capital R and then you have said small s. Now, there is a difference between capital R, small r, capital S and small s. So, question is not clear, but I can elaborate on this, that what is RS nomenclature? RS nomenclature is that if a carbon is there which is attached to 4 different groups, and then you what you do in the groups, you assign priority, and the priority rule says that first you try to check what is the, suppose this is Wedge, this is fluorine, this is chlorine, this is bromine. Okay. Now, you assign priority. The priority sequence rule says that you first check that whether the atomic numbers are different. The higher atomic number is given priority over the lower atomic number groups. Okay. So, here bromine has the highest atomic number. So, that is given the number 1, followed by chlorine number 2, followed by fluorine number 3, and then oxygen number 4. Okay. then the rule says that you have to see this carbon from a side away from the fourth group. Here the problem is the fourth group is actually towards you, towards the observer. The observer is looking from the top and the fourth group is also on the top. And so, now there are some tricks. First of all, the basic rule says that you have to look it from the downside, because from the bottom side 4 will appear away from it, but which is you cannot do. You cannot go below the table and to see this molecule. Okay. Since that is not possible, now you have two options. First option is you do again you try to bring the fourth group in the alpha position. If you want to do that, again that exchange in a group of 3 is also applicable in the Wedge formula. In fact, exchange in a group of 3 is available, is applicable for any projection formula. So, you do it in the Wedge formula also. So, what I do? I bring the fourth group at the alpha position, I bring the exchange in a group of 3. So, 3 goes here, 2 goes here, and fourth group comes to the down. So, fourth comes down and then 2 is here. So, 2 becomes here and then your fluorine comes here. So, that becomes your 3. So, you have done the exchange in a group of 3 and your bromine remains, you have not disturbed the bromine, that is number 1. So, now you whatever you are seeing, that is your absolute configuration 1, 2, 3. So, that is our configuration. Okay. The other way to do it is, if you do not want to do this operation, you look from the top, that is okay, check the direction is anti-clockwise, but since you are looking from the side of the fourth group, so it will be just the opposite what you see if the fourth group is alpha. So, you look from the top and see from the side of the fourth group, if that is the situation, then you change the direction whatever you are observing. So, 1 to 2 to 3 is anti-clockwise, but since you are looking from the top and the fourth group is towards the observer, you change the direction. So, it is looking as anti-clockwise, but the actual it will be R, and that what we exactly got after this rotation. Okay. Now, it is up to you whatever you want to do, but if you do this, you have to mention in the answer script, means we have MCQ type answer. So, there is no questions. So, that is not a problem, but if you have to describe these things, then you have to always mention that I am looking from the top and I am changing whatever I am seeing, because the fourth group is towards the observer. Okay. The next question is by Basudha Dev, okay, sorry, about conformation. So, you basically you want to know what are conformations, the general concept about conformation. Okay. So, what I said, I started in the lecture, I started with a double bond. Okay. Suppose you take ethylene kind of thing, a substituted ethylene. Okay. Now, in this case, what is happening, because you have this carbon carbon bond which is connected by a double bond. So, this you cannot rotate. This carbon carbon bond you cannot rotate, because the moment you try to rotate, the double bond will break. I can show you here. See, this is the thing, double bond, you can see. So, the moment I try to rotate, the bond will break. So, this is called a rigid system, you cannot, there is no rotation between this carbon carbon bond. Okay. But on the other hand, if you have a carbon carbon single bond and then you have 3 groups here. Okay. The moment you have that, then what happens? This carbon carbon single bond you can rotate, because you do not have to break any bond while doing the rotation. I can show it. See, this is the sp3, that means this is sp3 carbon, that is also sp3 carbon, the other one. Okay. So, now you take this, I have already shown this one that you cannot rotate this, because it breaks, it bends and breaks, and here there is no problem. You can just take this, it is freely rotating without breaking any bond. So, as you do this rotation, keeping one carbon fixed suppose, and the other carbon you rotate, you get different type of forms, okay, and different types of dihedral angles between these individual bonds, and these innumerable or infinite number of these forms are called conformations. The bigger question is what happens to the energy of this, because the energy keeps going up and down, up and down. So, basically you have energy maxima and energy minima, and I have already told you that the form that is the occupying the minima, they are called conformers, but every form is called a conformation. So, number of a conformer, again I just tell you the ground reality, that is all conformations are not conformers, but all conformers are also conformations. Okay. The next, let us see what is the next question. The next question is, alkene with 4 different substituents does not have improper axis of symmetry, then why it is chiral. Okay. Now, let us draw an alkene with 4 different substituents. Suppose this is A, this is B, this is C, this is D. Okay. So, 4 different substituents, but I take here. Okay. So, there is a blue and there is a white there, the red. Okay. So, I put 4 different substituents in an alkene. So, you think that this has no symmetry, improper symmetry. It appears to be like that, but you are forgetting one thing, that this molecule is a planar molecule. So, all these atoms here A, B, C, D, including these carbons, they are all in the plane of the paper here, and that plane of the paper becomes a plane of symmetry of the system. I can show you in the model. So, this is an alkene with 4 different substituents, but it has got a plane of symmetry which is like this. So, if you cut, if you have a plane which is containing all the atoms like this, okay, and that becomes a plane of symmetry. So, all planar molecules, keep in mind, all planar molecules are achiral if it is a plane, okay. And that is the basis of starting of the initially when people were confused that why tartaric acid exists in different forms. So, then it was Van 't Hoff and Lovell, they said that carbon must be tetrahedral, then only that is non-planar, then only you can have this stereoisomerism, this enantiomerism. But if it is planar, then it cannot show chirality. What it can show is the what was known as geometrical isomerism. Now, we call that as diastereomer. So, you can have another form where where B is here, A is there. Okay. So, these are 2 forms, okay. And you assign E z, you know the E z according to the priority sequence. Suppose this has got higher priority over B, and this has got C got higher priority over D. So, this is 1 2, this is 1 2. Do not make it 3 4, because you have to individually assign the priority of these 2 and then see whether 1 and 1 are on the same side. Earlier it would have been called the cis, but now that is what is called, this is the Z isomer, okay, and this is the E isomer. So, that you should remember that ethylene, even an alkene with 4 different substituents, are not chiral, except if one of these atoms A, B, C, D contain a chiral center, then only it can become chiral. Okay. So, what I am saying, if A is suppose a carbon CH, OH, CH3. That means you are introducing a chiral center, then only it can become chiral. Otherwise, if there is no chiral center in this molecule, in alkene, it cannot be optically active. Okay, it cannot show chirality. না আরেকটা আরও আছে একটু আর এসছি কোশ্চেন আচ্ছা নেক্সট কোশ্চেন ইজ what are point groups? Okay. What are point groups? I have already introduced to you the different types of symmetry elements. Point groups is basically a way to describe the geometry of an object or a molecule based on the symmetry elements. Okay. What are the symmetry elements? C, n axis, n fold simple axis of symmetry. Then you have the sigma plane, that is the plane of symmetry, you have I, and you have alternating axis of symmetry S n. Okay. So, based on these, whatever is present, what are the symmetry elements are present, based on that we assign the we express the geometry of that system in terms of some notation, and that are called the point groups. Like if there is some molecules which are called Cn. Cn is a point group. That means it has got only n-fold simple axis of symmetry, okay, nothing else. If you put Cn say V, Cnv, that is another system, that means that contains n C axis, and it also has a V here is indicates the plane of symmetry. Okay. So, plane of symmetry can be two types, one could be in the horizontal direction or perpendicular to the C axis, or it could be along the C axis. So, based on all these parameters you describe the geometry in terms of point groups. So, that is what is point groups. Again I repeat, point groups are a way to describe the geometry based on the symmetry elements present in the molecule. Okay. Now, the next question is by Gaurav Vyas. Okay. What are some exciting topics are there for cutting edge research in stereochemistry for a person with a background in physics and mathematics? Okay. Very good question, because nowadays we hear that interdisciplinary science. Okay. Interdisciplinary science means physicists doing chemical works in chemistry, and chemists are contributing to the area of physics, biologists are contributing to the area of chemistry, and vice versa. Okay. So, here we are talking about a person coming from has physics or mathematics background, what he has to do with stereochemistry, what is the research. Now, very interesting question. The most important area of research in stereochemistry is the origin of chirality. See, you know that in life, means all living systems are made of molecules which are say proteins or which are DNA, nucleic acids, all these, and these are made of chiral molecules. Okay. And in proteins, let me just extend a little bit. In proteins, the molecules have L configuration, capital L. Okay. And if you translate that into RS, except for cysteine, all are having S configuration. The question is that if you try to synthesize a molecule, and a molecule with a chiral center, and in the laboratory, what you will get is a plus minus mixture, 50-50. Okay. If you want to make one over the other in excess, which are called the stereoselective reactions or asymmetric synthesis, then what you have to do? You have to use one chiral, you have to introduce some chirality in the system. Now, how can you do that? You introduce chirality either that could be existing in the molecule itself, and you are generating a new chiral center, that is one possibility. So, the chiral center, existing chiral center controls the generation of the chiral centers, which can have R or S. So, it controls whether R will be formed or S will be formed. Okay. Now, or you can use a chiral reagent, your reagent may be chiral, that is also possible, and then as you have in chirality in the reagent. So, that will produce different ratios of the chiral molecules. Third is you can use a chiral solvent. Whatever you do, you have to have some chiral environment, either it is already inbuilt in the molecule or it is from the solvent or from the external reagent. But the question, bigger question is where from this chirality first chiral molecule is generated, because to make a chiral molecule you need chirality. So, the origin is basically the question is what is the origin of chirality. This is a very fundamental question to be yet to be solved. Okay. And this is also connected to origin of life, because life also originated from either who actually came, it could be nucleic acids or it could be proteins which first appeared on earth, okay. But they are all chiral molecules. So, the bigger question is this is connected, until chirality is generated life will not be generated. Okay. So, origin of life and its implications on origin of chirality, that is a very big question, challenging question, and it can be tackled from angle of physics, or one can do mathematical calculations from different angles, because there are certain things called parity violation rule, you can explore that. And for chemists they are also exploring, lot of people are exploring on the origin of chirality. There are various hypotheses, nothing has been proved. Okay. Next question is, I am finding chemistry little bit tough. Is there any way so that I can get ease in the subject? Okay. We actually started this course thinking in mind that it will span from first year undergraduate for the undergraduate students, first year, second year, third year, wherever they are. Okay. Now, we begin with the aspect of stereochemistry, which is taught in most of to the first year undergraduates. Okay. So, it started with the first year undergraduates, and then it went little bit on the higher side, but the overall topic is covered in the undergraduate chemistry. We have not gone beyond that. The best way is that do not jump from one topic to the other until you have understood the previous topic. Go through the lecture carefully, and then once you have understood everything, then go to the second lecture. Okay. And if you can't understand, throw question in the forum, and that will be promptly answered by the TAs. Okay. And here is the last question, that is, sir, I could not register. Now, this is the date is extended 17th November. This is an issue which we cannot help you. You have to write an email which is nptel@iitm, that is madras.ac.in, and I think they are going to help you out in this regard. Okay. nptel@iitm.ac.in. Okay. So, these are the questions that came to us. Now, refer some, one is book for stereochemistry, refer some books for beginners. Okay. That is now the book I suggest, say stereochemistry books are written, famous books are written by well known stereochemists, like the book of Eliel, the book of specialized book by Professor Noshipuri. He used to be here in IIT Kharagpur, and there are other books, but these are books on specially on stereochemistry. So, I will suggest that better you consult first a general book on organic chemistry, and then go to the topic in stereochemistry. Like if you know the book of Claydon, organic chemistry, and see what is written there about stereochemistry, or a book by Paula Bruce. that is also organic chemistry. So, what I am suggesting that better first go through these books, because they will write in, they are not stereochemists as per say, but so they will write in a very simple way and explain different things, and then you can go to the books by LL or by Professor Noshipuri. These are the two books I can refer. Okay. Review on alkenes and biphenyls. Okay. Now, there was one question, there are some questions in the discussion forum from where I find that there is some confusion in the, there are some confusion in the, while drawing the, while assigning the R S nomenclature in biphenyl and also in alkene system. Okay. Now, what is an alkene? An alkene is, this is called cumulated double bond, two double bonds side by side. Okay. This is your sp hybridized carbon, this is sp2. So, this will be like this. Interesting thing is that unlike ethylene, where all the bonds are in the plane, when you put another bond like alkene, now this bond, these two bonds will occupy a plane which is perpendicular to the plane occupied by these bonds. Okay. Now, I can show you the alkene in the model. Yes, I think that is the alkene system. Let us see. So, these two blue atoms are in the plane of the paper, but these two green atoms are, one is going below, another is going at the top. Okay. So, basically these planes are orthogonal. So, sometimes people say that alkene is nothing but, it is like a tetrahedron which is elongated. If you elongate these atoms and then you get these two atoms, and on the other side also you elongate and you get these two atoms. But remember, in tetrahedron also the similar looking beta alpha here and on the planes here. Now, if you elongate this center and take it here and elongate this center, take it here, what you end up is alkene. Okay. So, that is one aspect of alkene. The same thing happens in biphenyl. Biphenyl, if you have two phenyl rings, if you have two phenyl rings and if you have quite bulky groups here, suppose Y, Y. So, there, if that is planar, then they will hit each other. So, what happens? They also assume a conformation like this, perpendicular to each other. Okay. So, again the similar situation happens, the plane occupied by x and this x and y is perpendicular to the plane occupied by this x and y. Okay. Now, the question of assignment of RS configuration. First of all, alkenes become optically active if these groups are different, say AB, AB. It does not have to be this may be similar to this may be similar to this, but the important point for it becoming optically active is A not equal to B. So, if that happens, if that is the case, now you how do assign the configuration. Okay. Now, that CIP system, that is the Kahn-Ingold-Pirog system, they introduce the RS nomenclature. So, they say that you look from any of these from any of the side. Suppose I look from this side, keeping myself perpendicular to the plane of the board. So, that means my head is going up and my leg is going down. Okay. And on my right side, right hand is on this side and the left hand is on this side. So, I am looking from this side. If you do that, this carbon you have to give preference over this carbon, because you are looking from the side of this carbon. You can do the opposite also, you will get the same result. If you look from this side, then this carbon gets priority over the other carbon. Now, what does this priority means? Priority means that this carbon is giving priority over that carbon means these two groups will be assigned 1 and 2, and these two groups which are behind, which are away, they will be given 3 and 4. So, that is, suppose A is having a higher priority over B. So, you have 1 and 2 here, and now between this A and B you give the other two numbers, that is 3 and 4. So, this will be higher priority over this, but do not give 1 2 because you are not seeing from this side. So, there will be 3 and 4. Now, as you are seeing it, you draw how you are. So, these two will be towards your horizontal side. Okay. So, you get this form, and these two will be on the vertical direction. Okay. Vertical direction, and now you put the groups. So, that is your 1 which is going on the right side, this is your 2 that is going on the left side, this is your 3 and this is your 4. Okay. Now, what happens between these 1 2 3 4, you see the direction here 1 2 3. So, this has got R configuration. Now, one question I have seen in the discussion forum, they are saying that suppose what happens, suppose this becomes the drawing can also become that this will be bold. If you look from this side, exactly that can happen. So, if that becomes bold, means that is in front and that is at the back, the horizontal direction can be at the back. Okay. That is possible. Now, because this is bold, so that has to contain 1 and 2, and because this is on the back side, so that will contain 3 and 4. So, you put any of these, suppose 3 is here, 4 is here. Now, some people are confusing this one with the Fischer projection formula. Remember that this is not a Fischer projection formula, this is one. So, whatever you see, that is you are seeing away from the fourth group. This is not a Fischer projection formula. In Fischer projection formula, what I said, that if the number 4 group is occupying the horizontal position, then whatever you see, you have to change that or bring the fourth group at the vertical position. But here you do not have to do that, because this is not a Fischer projection. Okay. The fourth group is always away from you, irrespective of whether it is occupying the vertical direction or it is occupying a horizontal direction. The same thing happens here in biphenyl. Okay. So, when you look from this side, again this will be given, suppose 1, this is 2 and this is 3 and that is 4. That means, whatever you see, whatever projection formula you write, see, if I see from there, that means this will go to my left. So, that means you have this picture, this will go to my left, that means this is 1, that is 2 and this is 3, 3 is going to the leg side and this is up, and so that is your 4. So, whatever you see 1, 2, 3, so that will be your configuration. So, this is our configuration. So, that is the most important point. Let us see what are the, sir, not getting the view of the chair form after rotation, view of the chair form after rotation. Now, that is the question. Chair form is this one. Suppose I draw a chair, okay. You number it 1, 2, 3, 4, 5, 6. Now, if you rotate the chair form, now rotation in which, along which axis? Rotation along the, this is called the, you have a C3 axis, no? Or you have a A6. So, you can rotate it by say 60 degree. So, if you rotate it by 60 degree, so what will happen? So, that is why I gave you some mnemonic device, that rotation, many people get confused by this rotation. Let us see if we can take this, keep 1 here, because then that will become your number 1. So, your problem is that if you start with a chair, what is that? No, if you start with a chair, yes, if you start with a chair form like this, okay. So, it looks like, so that means at C1 you have a blue, is have a methyl. Okay. Now, you rotate it by 60 degree, you rotate it by 60 degree. So, I do that. If you rotate it by 60 degree, you see the chair form looks like this. So, chair becomes kind of a mirror image. So, whatever chair you have drawn earlier, now it becomes a mirror image of that. Okay. So, you write this. Okay. The question is, where is that C1? Actually I rotated in this molecule in the anti-clockwise direction. Again I start from the very beginning. This was the beginning starting conformer, and now I rotate it by 60 degree. So, if you bring it to like this, so you get a mirror image here, and your C1 is here, that is the methyl. Okay. Now, you again, so this is 60 degree rotation. Remember, each 60 degree rotation the chair goes to the mirror image of the previous one. If you remember, then that will be okay, that is best, and then try to identify at least one of the center. Once you identify one of the center, like here I have put a methyl. So, I just concentrate on C1. So, C1 is now after 60 degree C1 has come here, and now it is easy to put the other numbers, because the directionality does not change, that 1, 2, 3, 4, 5, 6 will remain the same 3, 4, 5, 6. Okay. So, this is the situation, and then if you further rotate another 60 degree, you see you will get the again the chair form which looks like the first original one, but what I said that by each 60 degree rotation you get the mirror image chair form of the previous one. Okay. So, when you did another 60 degree, the chair will look like this. Okay. The chair will look like this. Now, where is the methyl? The methyl is here, because remember by rotation these are the top carbons and these are the bottom carbons. They do not change their nature, top carbons remain at the top and the bottom carbon remains at the bottom. So, in this fashion you can do the rotation. Okay. If you are because sometimes you need to do this while comparing different systems. Okay. I hope this is clear. So, the ground rule is that you draw the after each 60 degree you draw the mirror image of the previous one, identify one center where it is now, and then do the and put the other carbons. Okay. So, how to find number of stereoisomers in a molecule? How to find number of stereoisomers in a molecule? Now, what type of molecule, that is very important. Okay. Number of stereoisomers in a molecule. Suppose you have a molecule where there are several chiral centers. Okay. Suppose this is one chiral center, that is another one, that is another one. I am saying chiral center, remember these days people do not say chiral center, they call it stereogenic center. Just for simplicity, I am calling it chiral center. So, the general rule is that if these chiral centers are all different types, that means suppose this is OH, this is Cl, this is Br, this is I, this is F, and this is methyl, this is hydrogen, this is ethyl. So, now every chiral center is different, they are not same. So, the number of isomers that you will get will be 2 to the power n, okay, will be 2 to the power n. So, the number of stereoisomers will be what? 2 to the power 3, that will be 8. So, that is the general. If a molecule has n number of stereo centers, then the formula is 2 to the power n. However, when you have similar chiral centers, similar means constitutionally similar chiral centers, then the number of stereoisomers they are reduced, okay, because then the question of meso compound comes. Like suppose you have a molecule which is like this, you have CH3, you have CH3. So, I draw one form OH here, OH there, H here, OH here, H here, H here. So, this is a molecule which has 3 centers again, this is a center, this is a center and that is a center. So, these 3 centers. Okay. Now, what will happen? These 3 centers, earlier formula says 2 to the power 3, it should have 8, but now it will not have 8, because there will be some mesoforms, optically inactive forms. So, that corresponding mirror image will not be there. Okay, I will also tell you, among these 8, they will exist as 4 DL pairs. There are 4 DL pairs. Okay. That means 4 different plus minus compounds. Okay. And here the number decreases, because you have to see this is whether this is chiral or not. Now, this molecule is chiral, because this does not have the, here it is usually we look at the plane of symmetry. This center is constitutionally similar with this, because it has got a wedge HCH3, this also have H wedge CH3. Now, if you bisect it, you do not see the plane of symmetry. Okay. So, it has got a mirror image. So, that is number 1 and the mirror image is number 2. Then you have another form where you bring the wedge here, keep the wedge there, keep the wedge here, H CH3. Now, this has created a plane of symmetry. Okay. So, if it has a plane of symmetry, so that means it does not have the mirror image will be same. So, this is your number 3, and then you can have another meso compound which will look like this, which all 3 wedges are on the same side. Okay. And so, that is the number 4. See, the number of isomers has drastically reduced in this case. Okay. So, there are certain formulas that are given, you can find that if there are n stereogenic centers like that, then it should be 2 to the power n if all the stereogenic centers are different. If 2 of them are same, then that is one formula. The bottom line is that the number of isomers then drastically reduces. Okay. Sir, how to, the another question has come, sir, how to know whether a compound is resolvable or not? Is resolvable or not? Okay. That means, you are thinking that we have a DL mixture or plus minus mixture, whether we can resolve it into not. So, that is the process is called resolution. Okay. So, a racemic mixture and going into plus and minus. Now, this will be resolvable only when these plus and minus do not interconvert readily. If they interconvert very readily, then you will not be able to separate these molecules. Like I gave you an example of cis-1,2 dimethyl cyclohexane, where what happens? The mirror image is non-superimposable, but the problem is they do equilibrate to each other by a process called flipping. So, your short answer is that they will be resolvable if the D and L do not interconvert at room temperature. Okay. So, this resolution we are talking about room temperature. If you lower the temperature down, if you can slow down this equilibration process, then it might be possible to separate them. Okay, thank you very much. So, we look forward to the second the live session sometime later. Okay.